one other thing about rate laws before we talk about how to determine them is that the units for the rate constant k need to be such that our rate is in terms of moles per liter times second, assuming we express all of our concentrations in terms of molarity, which we usually do. So whatever will give us units of moles per liter per second, that is what K will be equal to. So it depends on the specific rate law what the units of K are going to be. So you just sort of have to work that out depending on the specific rate law you end up with for a given reaction. Okay, so how do we actually figure out rate laws? So again, looking at our generic reaction, A plus B with their stoichiometric coefficients goes to Y plus Z with their stoichiometric coefficients. In general, we'll assume that our rate law will have some form where we have K times concentrations of our reactants raised to some exponent. So we'll have A and B, and we'll assume Y and Z don't matter. And generally, there are very few exceptions where they can matter if they participate in the intermediate steps of the reaction. But in general, you can just assume it depends on the reactants. And as we saw in the previous videos, sometimes these exponents can even be zero, right? It can not depend on the concentration at all. Okay, so I want you to pause the video and think about how would you determine the rate law for a reaction. Okay, so hopefully you took the time to pause and think about this, made some notes to yourself, hopefully. And we'll go ahead and talk about some specific ideas here. And probably you have done some experiments like this before in either general chemistry, and definitely you will or have done it in our class as well. So there are a few different specific methods. One is the method of isolation. And the idea behind this method is we pick one of the species and have it present in a large excess. And the idea behind that is that if you have an excess, even as the reaction goes on, that concentration will stay constant. So let's say our example here with A and B. If we have lots of A, then the concentration of A, even as a function of time, will be approximately constant. So a little bit of A is going to react and form products, but most if there's not very much B for it to react with, not much will change. And what that lets you do is change the concentration of B and monitor that and see how does that concentration affect how fast things go. And then you would switch. Then you would switch to see if you have a lot of B present and its concentration is fixed. You can then vary A. So you're essentially isolating one of your reactants at a time. So start with lots of A, only a little amount of B, measure the change in the concentration of B as a function of time, and then switch. And then that lets you see how do things change over time in terms of the concentration, which can let you determine the rate. Another very common method, and the one that we used in our lab, or will use in our lab, is the method of initial rates. And the way this works is that we don't necessarily measure the full course of the reaction. We instead say, okay, well, let's say our rate of change in concentration A with respect to A, we can say that is approximately equal to a macroscopic change that we can actually observe, a delta concentration of A over delta T. And these are, we can have a fixed amount of concentration that we're monitoring and, just measure the time with like a stopwatch or something like that. And then what we would do is then do this for each of our reactants that we care about. We would change the initial concentrations and see how those initial concentrations affect the rate that we measure. So this is the method of initial rates, that we measure the change at the beginning of the reaction and not necessarily monitor the whole course of the reaction to see how the reaction proceeds. So that's why it's called the method of initial rates, because you only look at the beginning of the reaction and you make the assumption that derivative can be approximated as a delta, as something, a macroscopic change that you can actually measure. One other method, and that we can do for very fast reactions, these types of strategies are sort of difficult to employ because maybe your reaction happens on the millisecond or nanosecond or microsecond time scale, and you can't really watch it in real time necessarily. There is another general class of methods called relaxation methods, where you have a system at equilibrium and you make some sudden change to it that changes the equilibrium, and you measure how quickly the equilibrium is reestablished, and that tells you how fast that reaction is happening. So things like, you can change things like temperature. So there's things known as a temperature jump experiment, where you suddenly increase the temperature using some external way to change the temperature, like a high-powered laser or an electrical heating that can also cause a temperature jump. You can also do things like change the pH. If your reaction is pH dependent, you can do a pH jump where you suddenly change the acidity or basicity of your system. And you have some way of monitoring concentrations on a pretty fast time scale. So often through spectroscopy or other ways of doing this. So these are some of the methods that are used to determine rate laws so these are experimental methods used to determine rate laws for reactions.